Good evening, everyone. We're going to get started just momentarily. If you have not set up a Microsoft account, please go to account.microsoft.com and do that while we're getting started. We're going to be using an online service through Microsoft's Azure Notebooks. And so this is the URL, and we will paste that into the Q&A chat for you as well. But that's what we're going to be copying. Welcome to a Microsoft Reactor discussion about machine learning. We are going to be focusing on developing machine learning models. And this is normally a one-day full class, and when things are in hopefully more normal situation, you'll be able to take the entire version, but we're going to focus just on some data cleansing and machine learning model interactions as part of our discussion today. My name is Brian Sletten. I'm an independent software consultant working with Microsoft, and at this point I've probably trained close to 3,000 people around the world on machine learning. And it's a very exciting time to get into it. So we're going to talk a little bit about the process of getting online as a machine learning person with data science and things like that. But if you have questions, feel free to reach out to me on Twitter, and I'm happy to have conversations after this is over as well. So the Reactor program is a collection of physical locations around the world that Microsoft has set up to work with developers and startup leaders and meetups and things like that to encourage community-driven classes, and it's a space where people can come together and collaborate. So normally, again, under normal circumstances, this is a great place to go and hang out in person. But through this Reactor program, we're doing these live online training sessions now too, and hope you find them interesting. Definitely go to the calendar near your location and see what things are coming up. There's a variety of events that are available in an ongoing basis. So we're not going to assume a lot of background with machine learning today. But we're going to walk you through some of the basic ideas, a little bit of background to data science, which is sort of a way of institutionalizing kind of the scientific method to how you go about learning from your data. Because one of the things that I want you to take away from this is that you cannot just simply plug numbers into algorithms and hope to get any kind of meaningful result from it. We have to understand how the data is collected. We have to understand the shape of the data. We have to understand a bit about the distribution of the values in the data before you can hope to benefit from the second part of this, which is going to be the machine learning models. So we're going to focus on the first three sections, but there are, again, as I said, other tools and things that are available and courses that are available to you as well. All these sessions are also available through the Microsoft GitHub Reactor page. So you can check these things out and work through them on your own as well. So the goal is really just to be a useful way of exposing you to kind of new ideas and the new technologies that are emerging that are very exciting in our field. And if you're not from the tech space, but you're interested in getting into it, there's some really great paths for getting into that, learning paths to get into that as well. So this is my first time doing the Reactor through Teams Live. I do appreciate your patience as we sort of work through any hiccups. There is a question and answering mechanism through the Teams app. If you ask questions, they will show up to me, but I'm also giving the presentation, jumping around. So we will try to make sure that your questions are answered as quickly as possible. Feel free to chime in throughout the course. but I will also leave some time at the end of the discussion to go through questions, or if there are any further answers or any further issues people want to discuss as well. So, without any further ado, normally there's a movie to show, but because the bandwidth I think might be a little bit tricky, we're not going to do that. But it highlights the fact that a lot of the motivation towards moving towards machine learning is being driven by kind of a combination of events, right? It's an explosion of data. Data is growing at a rate that is just almost inconceivable. I read a study from Berkeley from the early 2000s that said, from time t equals 0 to about 2002 or 3, humanity had created roughly 12 exabytes of data. And now I saw a video of a woman who was discussing complex serverless architectures as a geneticist, and she said by this year she's expecting to have her one project to contain 20 exabytes of data. And we see projections that by the year 2025, we'll be dealing with like 147 zettabytes of information and data. And just to be clear, a zettabyte is a trillion gigabytes. So that is a lot of data that has to be stored and indexed and be searchable and be accessible somehow. And so what we're seeing is a lot of this is coming from sort of traditional data sources, but we're also seeing the emergence of things like agriculture and manufacturing and biology that are being used as inputs, so that manufacturing processes can be analyzed. We can try to look at the quality of what's being produced to maybe root out any manufacturing defects in the process. From agriculture, we're trying to maximize the productivity of individual farmers by giving them inputs from things like temperature sensors and humidity sensors, and allowing them to define sort of very targeted, focused reactions to the conditions for their fields based on their orientation and whatnot. So it's this integration of traditional data sources as well as new sources in the form of Internet of Things devices and other capabilities. Now, we're also seeing an explosion in terms of the quality of cameras and microscopes and things like that. So science, at a time when many scientific budgets are being cut, are producing orders of magnitude more data than they've ever dealt with in the past. And so we're trying to have machine learning be part of the process for helping us deal with that explosion of the data, because we simply don't have enough people to stay on top of that growth. And so we're going to have to rely more on the software to do that as well. Coincident with that is the ubiquitous availability of things like smartphones and tablets and other communication equipment that people now carry with them all the time. And while it's how we've learned to communicate with our family and friends, this is also opening up new opportunities for people with different abilities to gain more out of their environments. I've seen some really fantastic projects that Microsoft has to, say, allow a blind person to hold up a camera and be told something about the nature of what's going on, or you're talking to a male in his 30s and he seems to be happy, right? So we're able to treat these phones as sources of information. And in doing so, we have to be considerate of the sensitivity of the privacy of the data. So if we're dealing with something that's medically oriented, we might not want to get it off the phone. So the point is, where data comes from is changing. Where we want to be able to reason over data using machine learning is also changing. It's not just on computers in the back end. It's also being pushed to edge computing devices like mobile phones and Internet of Things sensors. So there's just a lot going on, and we're gaining new tools to help us interact with that. So I mentioned data science as being sort of this cross-disciplinary way of approaching the problem of trying to learn from our data. If you are not careful with how your data is collected, then there could be bias in the data collection process that gets entrenched in the models, and we want to avoid that if possible, but we certainly want to detect it. So generally, we see this intersection of statistics, which gives us the capacity to reason over populations, to analyze distributions of data values, and it's a fairly wide cross-disciplinary approach that has been used for many years by people that we would just traditionally call researchers. So researchers have domain expertise in a particular field. It could be like nutrition, it could be economics, some kind of social sciences or biology. And the data collection process is tricky, right? So they have to figure out how to collect what they can and then determine, is that sufficient as a way of representing the population that they're trying to reason about. If you're trying to look at nutritional impacts, you'd have to look at a variety of geographic locations, various economic levels, just to sort of make sure that you're not collecting information just about sort of wealthy people and then trying to reason over the health implications for people who maybe are living at a lower subsistence level. So statistics helps you deal with the fact that data collection is tricky, and you want to know, do you have enough to draw the conclusions that you're drawing from, then applied to a particular field. We would call that traditional research. Now, what's happened in the last 10 or 15 years is we've seen this explosion of data sources. So again, Internet of Things devices allow people to create some really fascinating ways of collecting information. One of my favorite things I was exposed to in my becoming more familiar with the Reactor program and what Microsoft was offering is discussed at a site called wildbook.org. It is a multi-party collaboration to help researchers studying migration patterns of animals and things like that, but they're mixing in image classification to be able to identify animals based on their stripes or spots in the wild. So historically, they would have had to sort of parachute in and tranquilize the animals and tag them somehow, and maybe try to trace them from the air, and then catch them again. And that's just it's traumatic for the animals. It's tricky. It's expensive. But now they're able to use like image classification from images that are showing up on social media when people go on safaris or whatnot and take pictures of particular animals. Then they are able to sort of, oh, hey, that's one of our zebras, and that's one of our elephants or something. So that's again producing all of this data, but people who are traditional researchers don't necessarily have the skills to deal with that much data, or to deal with the computational demands of dealing with that much data through cloud computing, hardware acceleration, through things like GPUs and whatnot. So data science is really this intersection in the middle that brings together these various disciplines. The people who understand the domain, the people who understand how to reason over populations, the people who understand how to collect and analyze the magnitude of data and deploy that into a running system. And that skill is what we're centering on as data science. And if you're coming to this, again, from a learning experience, it could be overwhelming in terms of how much you actually have to deal with. And the good news is nobody's an expert in everything, right? You can't be a biologist who also understands statistics and is also a computer hacking genius. So when you're thinking about becoming a data scientist or a machine learning expert, consider you're part of a team, right? And the team is going to have these skills, but you as an individual don't have to have all the skills. Usually some kind of combination of statistics and programming, or research and statistics. That's where you'll find most people hang out in this field. But then teams will be brought together with people from the other elements to bring it into a successful functioning team. So data science, again, is really just sort of a procedural grounding in the data collection process of these various elements. So if you're talking about some kind of enterprise software or some kind of offering that your company wants to do, there will usually be some kind of business motivator. Why are we doing this? We're trying to understand where the customers are coming from. We're trying to understand their buying habits. We're trying to understand migration patterns of zebras in northeastern Africa. Whatever it is you're trying to do is what's going to drive the activity, right? Nothing happens in this world without some kind of motivator, right? Because it takes time and money and costs quite a lot to do this effectively. So when you're doing these things, you need to understand why you're doing them. And there's two main reasons for that. And that's because you're either going to be rolling it out into a product, in which case you have to consider the implications of the product. You have to consider, is this going to be something that runs on a phone? Well, then the models that we create can't be enormous models, right? If the models are enormous, then we might need to store them in the cloud through Azure services or something. But then we have to worry about, well, is somebody going to interact with them through a phone, in which there are latency issues now? So, we have to make sure that the thing that we're building makes sense and is going to make sense in the context in which it's deployed. The other main driver of these kinds of activities is asking of questions, like, why are customers behaving the way that they are? Well, you need to have data to drive the discussion. So we collect data, we build some models to analyze it, but then we need to tell the story to the stakeholders. And that process of telling the story can't be couched in very complex machine learning ideas, because business stakeholders are not generally going to understand them. And so if the whole purpose in doing something is to help convince somebody to make a decision, and if you can't explain it to them in a way that they understand, then that's not going to be adding any value as well. So understanding why you're doing something is crucial to this. Then you need to start collecting the data. And the data that you're collecting has to be representative of that problem. If you're building some kind of credit worthiness application or something, collecting somebody's favorite color is unlikely to be a useful approach, unless that color is blue, because those people are awesome. So we need to make sure that there is signal in the data that is correlated or somehow indicative of the outcome that we are trying to learn from. And so that process is not always super clear. We don't know where that signal is. As a quick example, 20 years ago, I worked for a company called Parabon. If you've seen the TV show Genetic Detective, you may be familiar with them from that. But we were building a platform for doing computational intermediation, aggregating idle time on computers all over the world. And one of the researchers that came to us was interested in using interferon A to treat fibromyalgia, but they couldn't explain why it sometimes worked and sometimes it didn't. And so we were able to expand the amount of data that they were able to look at and include things like whether people had onset of some kind of physical trauma prior to the administration of the interferon A. And that was just not something that they had expected to be part of the story, and so they weren't looking at that data. It wasn't until we gave them the ability to expand the amount of data that they were looking at were they able to see that was the signal that was driving the outcome. So that's where things like cloud computing capabilities allow you to basically start small but expand into a larger initiative if and when you have some kind of business driver in that sense. And so that's going to help you understand the data. And from there, then you can make sure that the data that you're collecting looks the right way, is shaped the right way, is consistent with the algorithm that you're trying to learn from. So once you gain some familiarity with the data, then you'll start to do some early efforts in trying to model the relationship between the things that you've collected and the outcome that you're trying to teach the software to learn. This is a type of machine learning called supervised learning. And the feedback mechanism helps us decide, oh, okay, we've collected some more data that changes the nature of the relationship a little bit. Okay, we've now got a pretty consistent view of what's going on. And that can help us draw some conclusions. So as you see on this diagram, there are arrows that point back to earlier stages. This is not necessarily a one pass through the process. This is a learning process, and you may have to revisit some of these things if you get to the modeling stage and are not able to make good predictions. Then there's probably an issue with respect to the data that you've collected, and again, you're trying to draw conclusions from maybe an insufficient amount of data or an insufficient variety of data. But once you get pretty comfortable with that process, then you can try to train off of the data and then try to evaluate how well did it do. And here's where it gets a little bit tricky. You may hear the term overfitting. That's generally equivalent to the idea of memorizing the answers, right? If you have a classmate in school who found the answer sheet and memorized the answers to a test, he would look like he did a pretty good job on that one test, and that's not necessarily an indication of learning. If you ask the same student a slightly different question, or a question that was not on the test that he memorized, then it would be pretty easy to see that you didn't actually learn anything useful. And so when we're evaluating the model, we're generally going through this process of I'm training on certain inputs and connecting them to certain outputs, right? That's called our training data. And that's the model learning process has full visibility into that. But then when I evaluate, I will plug the inputs of some test data that we haven't seen so far in there to our model, and that will make predictions. And therefore, what comes out the other side, we can compare to the actual values that are associated with our data. So that's how we can determine whether we're just memorizing the answers or not, or if we have actually learned something fundamental about the nature of the relationship. So we'll see some more of this as we get into some actual code examples. Now, you could establish that you've got a fantastic model, that it's able to make good predictions, that you've understood your domain well. But if you don't keep up to date, then eventually your data will start to deviate from that model. As an example, if you are trying to look at software sales, or even in the middle of a pandemic, right? Why did we see these logistics disruptions? It's because a lot of these supply chains were trained off of data and demand models that suddenly were no longer valid. And right, if your data is not consistent with what you've seen in the past, then it's not going to be able to continue to make good predictions. So as data changes, even if at some point in time you had a great model and a great understanding of things, you need a capacity to keep that up to date. And that's where the deployment model starts to come in. And this is one of the things, if you're new to machine learning, but you come from a more conventional data science background, then you will have the ability to, I think, make some good contributions, right? Because we as a discipline understand continuous integration, continuous delivery, DevOps, and things like that. The goal is to help you do that more seamlessly. So again, that's where a lot of the tools and the things that are emerging, like TensorFlow and PyTorch and Cognitive Toolkit and everything in this space, help you train, help you evaluate, and help you deploy in a fairly consistent DevOps kind of way. And so you may hear the term MLOps, that's sort of the machine learning specific flavors of DevOps. The slides should be available through the GitHub. If they're not there, I will track them down for you. I'm not in charge of exactly where they're stored. Sorry. We will get them to you, and I will show you how to do the Azure Notebook clone in just a moment if it's not clear. So thank you for asking those. All right. Now, as I said, everybody on the team is not going to have the same background. We're going to have some people who maybe are more focused on the domain, some people who are more focused on the development tools and techniques and everything. And so there's actually a wide range of roles. Anything from a data analyst that's going to be more focused on the particulars, down to a developer who, could, in theory, build a system on any kind of domain, but they don't have any expertise in any particular domain. And it really comes down to, along the way, a data scientist is somewhere in the middle, right? We need to have that boundary of, I understand the domain, but I also understand the process that we're taking. And since most individuals don't have all of that, that's where the team composition is so crucial. But in terms of helping along the process, a data engineer might be able to do some cleaning of the data to understand it well enough to look for missing values and whatnot. So the first thing that we're going to focus on is some tools to help you deal with the missing data. So that's another type of role called data engineering. So far we've identified there are domain experts, there are data engineers who work on the pipelines that feed the data into the training and operational processes, the data scientists who are involved in the selection of models and the tweaking of the models to get them to be as predictive as possible within a particular business context, all the way down to the developers who are writing the code, deploying these things into running systems. And you can find yourself, in any one of those fields. But one of the main reasons, obviously, that most people are interested in this space is because there's a lot of demand, and it's a very lucrative field. So the median base salary in the U.S. is about $130,000 for a data scientist. That's like, I think, 170, 180 in Canadian. So, all right. If you have not gone and created an account, please do so. Go to account.microsoft.com. There's no cost associated with this. It's just a way of allowing people to allocate resources, because you're going to be spinning up some notebooks in the cloud, and that's just something that they don't want to open up to anyone who hasn't sort of registered. But then we're going to be using a version of a Jupyter notebook, and I'll explain what a Jupyter notebook is in a second if that's a new concept to you, with some specific things to play around with. So this URL right here is the URL for the notebooks. If you can go to notebooks.azure.com, sgoodles projects data-science-2, there should be if you're logged in, there should be an option to clone the repo. If you have any issues with that, please let me know, but it should be pretty straightforward. So what that's going to do is that's going to take from Sarah's base notebook space and replicate it into your space. So now any changes that you make to the notebooks will not impact her, and you'll have your own sort of version of these to play around with. So once you go through the cloning process, you should feel comfortable to edit things and make changes with the knowledge that you're not going to be breaking anything for anybody else. This is going to be your view into these notebooks. Now, the notebooks themselves are experienced through a browser. As you can see, there are a series of controls. We've got a series of cells. The cells are the text fields down below, and those cells are either documentation cells or code cells. And I'm going to switch over from the presentation to this in just a moment, and I'll show these in more detail. But the code cells are, in our case, Python code, but Jupyter Notebook supports other types of languages, Java and R and things like that, with the right plugins. But without something like WebAssembly, they're not able to run directly in the browser. So on the back end, there's a server element that is going to be actually executing the individual cells. So when you execute an individual code cell, the text field basically will be captured, sent up to the backend server, it'll be executed, and the results will come back and show up in your notebook. So it's a very cool way of having people be able to interact with complex software and without having them to have to install a bunch of stuff. If you want to download these locally, you can also do that. There should be an option when people do the clone to if you want to play with these after the fact, but you will have to have Jupyter Notebooks installed, and that can be done against any Python installation, If you go to anaconda.com and download Anaconda with support for Python 3, you should be able to open those up here. VS Code has a Python plugin that allows you to execute Jupyter Notebooks within VS Code. So it'll basically spin up the server for you without you having to worry about it. But under the hood, these notebooks are basically just JSON files, and they're really ugly JSON files. So I wouldn't look at them, by hand. But because they are JSON files, they can be easily checked into your repo of some sort and checked back out. So it's an easy way to share narratives and tell stories around the interaction with data. So you could have documentation cells that say, here's why we're doing this, and here's a link to the Jira issue that asked for us to do this in the first place. And then here's where the data came from, and maybe have a link to where the data came from. And here's some transformations that we had to do, and here's the actual transformation. So as somebody's going through, they can just edit or run the individual cells and have an ongoing narrative here as well, without them having to look at source files and then have tools installed, with any kind of complexity. That's really why these are so useful, particularly for educational purposes. But within your typical organization, it's much nicer to send somebody a link to a hosted notebook and allow them to interact with it directly without having to have the skills to install and configure software in complicated ways. So we will come back to this, but just to be clear, the Jupyter notebooks that we're dealing with are hosted in the Azure environment. And so you don't have to deal with the running of the backends yourselves while you're using the hosted versions, because once you log in and once you start up the notebooks, it will spin up resources in the cloud to execute these for you. All right, so let's start with a discussion about manipulating and cleaning the data. Again, I'm just going to go through a couple of slides, and then we'll switch over to the notebooks. Python itself is very popular in this space because it's a very readable language. It's got a very clean syntax. It supports functional programming. It supports general, OO kinds of approaches. It deals with procedural programming nicely. So it's an easy language for lots of people from various backgrounds to use together without getting complicated. You can imagine a Scala or a Haskell or even C++ would be a lot trickier for maybe a domain expert to learn than say a Python. But part of that flexibility is also comes with a cost performance. And so Python itself is actually a terrible language for dealing with things numerically, absent the availability of a library called NumPy. So Python's engine is either, in C in most cases. There's also a Java version called Jython. There was a .NET version called IronPython for a while as well. But for our purposes, we'll focus on the C version. NumPy brings the ability to store the large data sets that we're dealing with down in the C level. So it's very efficient and able to iterate over large amounts of data with pretty low effort. The same equivalent of doing that up in the Python space is very, very slow. And in some case, it's orders of magnitude slower. So NumPy is the library that we're going to be using to deal with low-level data manipulation. And unfortunately, we don't have a whole lot of time to go into too many details with NumPy. There are other courses and plenty of online material that you can go through to teach you that. But basically, it's Python and then NumPy. And then on top of that is a library called Pandas that introduces the notion of a data frame. And the data frame is a very efficient way of slicing and dicing the data to focus on columns and rows and what's missing and combining multiple data sets together. Again, because this is only a 2-hour session, we're not going to go into all of the details here. But as you'll see when we switch over, after the data cleansing part of one of the notebooks, there's also additional code samples that you can work through. We're gonna focus on data cleansing and then look at some of the machine learning models in the second notebook. So Python, NumPy, Pandas gives us a stack for loading the data in over the network, reading them in from CSV files, things like that. You can reach out and run queries against relational databases. There are plugins for pulling data in from other sources. But then the machine learning part comes on top of this with a library called scikit-learn. And that is where the individual learning algorithms, whether it's the supervised learning stuff that we're going to focus on, like linear regression, the classifiers like decision tree classifiers or logistic regression classifiers, those are all implemented in scikit-learn. And that lives on top of the NumPy stack. It's not directly on top of the Pandas stack, but it's easy to move back and forth between them. And so this is a great learning stack for getting comfortable with machine learning and data science. Many organizations are not running Python in production, so you may not be able to directly translate the code that you write into production, but a lot of the models that you create can be ingested in something like a PyTorch or a TensorFlow, which then allows you to maybe serialize it out and read it into a version of their APIs that work with C, C++, JavaScript, and things like that. So, but there are several organizations. Spotify is an example of an organization that does a lot with scikit-learn in production. So we will address those accordingly. Now, why are we spending so much time in a 2-hour class discussing cleaning the data up? Because this is absolutely a garbage in, garbage out kind of scenario. If you train off of bad data, skewed data, the wrong data, then all the machine learning algorithms in the world are not going to help you produce anything useful or meaningful. So that's why we want to make sure that we deal with bias in the selection process, that we want to make sure that we have enough examples of the type of data that we're trying to reason over in the general population. And so Pandas is going to give us the ability to deal with that. So again, a data frame is generally, you can think of it like a programmatic spreadsheet. It's got rows, it's got columns. Once you have a data frame, and we'll see how to get one in just a second, you can call the info method on it, and it will print out a summary of the number of columns, the number of rows per columns, and you'll see that sometimes you don't have the same number of rows for every column. There just may be details you don't know about some of your samples. Generally, once you have a data frame that you've read in from someplace, you're going to want to see roughly what the shape is. So you can call the head function, and by default, that is going to show you the first 5 rows. There's also a tail function, which will by default show you the last 5 rows. So you can see how these things, in this case, we're dealing with a data set called the iris data set. There are 150 rows, and each row has 4 values representing some kind of measurement about an individual flower. So we know their sepal length, their sepal width, their petal length, and their petal width in those scenarios. And so the idea with a machine learning activity like this would be, maybe there's something about the distribution of values where one type of iris is more similar to each other than other types of iris based on those genetic variations. So in addition to knowing these individual features of our iris data set here, we also know what class of iris they come in. And so I'll know in this data set there are 3 classes. There's the setosa, the versicolor, and the regenica. So I can know which of those features are associated with which of those classes. Now, the missing data is something that we can deal with. In this case, you can create a data frame directly from a Python list, and Python lists can be heterogeneous. So in this case, we have a number, we have np.non, so it's the NumPy not a number marker, for something that is technically not legitimately a number. We have a string, and then we have the Python none object. You can throw those all into data frames, no problem, but you can't do math with things that aren't numbers. So if we tried to take the average value and we had some missing values in there, then this would throw errors. And you'll see this when we look at the code samples shortly. So if I want to print out a value in Python, I can just, in a Jupyter Notebook cell, the last element in the cell that's an expression will be evaluated. So in this case, example run would show us that we had a 0, not a number, an empty string, and none in there. If I want to know which of the rows have missing values in there, obviously it's easy when there are only 4 rows, but if we're talking about 1,000,000 rows of data, it would be very easy for us to miss those. So having a programmatic way of doing that would be interesting. So the isNull function basically returns true or false for indicating whether something is there or not. And keep in mind, we're dealing with a programming language named after Monty Python. So it has kind of a silly definition of truth. And basically, it's anything that's not 0 or false is true. So in this case, 0 is considered false. I'm sorry, in this case, not a number is considered false. But on normal Python, 0 as a numeric might be considered false in some scenarios. But for our purposes, a value of 0 is not considered a missing result. Therefore, it is not a null value. So the isNull function returns a Boolean value to indicate whether the associated row is missing something. So the first one is not missing anything. It is a number. The second one is not a number. Therefore, it is missing. The third one is not missing anything. It looks like it is, but it's just an empty string. Again, I can't do math on empty strings, but it's not considered missing. And then Python none is also considered a missing value. If I call the drop NA function on a data frame, it will drop any row that has 1 or more missing values on it. And as you imagine, this could be a fairly devastatingly destructive thing to do. So there's a lot of nuance. Once you get more comfortable with this, you can see drop them only if they're all missing values, drop them if there are no more than 2 non-missing values per row. Right? You can have complete control over what the drop process looks like. But in general, what we're showing are you've got the ability to analyze the data, look at it, what's missing, what isn't, and drop the missing values if they're going to cause you trouble. You may find that dropping the values is too complicated or throws away too much of your data, so you may want to fill in the missing values. And you have to be a little bit careful here because this could change the results of the analysis. If you're talking about like the average age of people who had complications with respect to COVID, and you just don't know what people's data is, you don't necessarily know what their ages are. If you just say fill in the missing values with a 0, obviously that would impact any kind of age-related studies that you wanted to do with the data. So other ways of filling in the values could include things like fill it in with the average value, fill it in with the most common value. And there's no right answer. All right, this is where you, as the data scientist or the data engineer, are going to have to use your brain to think about what's the right thing to do in this particular situation. We're just showing you that there's a mechanism through pandas to do so. The policy of how you enforce those is going to be up to you. And again, we're going to see these in action momentarily. Occasionally, you'll have duplicate rows. That's not necessarily a problem, but under some circumstances, it might be. Like you've got a data set here and a data set here, and you merge them together. There might be rows that are the same in both data sets, and you don't want them overrepresented in your analysis, so you could drop them. So in this case, notice A1 in row 0 and A1 in row 2 are considered duplicates. The first time we see it, it is not a duplicate, but the second time we see it, it is considered a duplicate. And then notice B3 back to back. First time it's not a duplicate, the second time it is. So once we drop the duplicates, just like you can drop missing results, then you will be able to have a unique per row set of data elements. And then the last thing before I switch over, I'm going to highlight, we're not going to do a whole lot with the concatenation of the data sets, is to kind of tie it all together. Pandas, in this case abbreviated as PD, has a function called read CSV for comma separated value file. And if you have a file that's available to you wherever you're running this, then once you read it in, it's going to automatically assign rows and columns to the data based on the shape of what came in from the file. If you happen to have tab separated data, you could still use the same function. There's another argument that defaults to a comma, but you can specify the separator character as being a tab or a pipe or something like that as well. So what we're going to do in a moment is we're going to read some data in. That's going to give us a data frame. The data frame we're going to be able to explore using the head function. Because this is numerical data, in this case, there's a statistics function called describe. And notice it's going through and saying for each of the features that we have, and this data set represents a Boston housing data set from the 1960s or 70s. The first column has to do with crime rates. The NOx column has to do with pollution levels. The RM column has to do with the number of rooms in the houses in a neighborhood. And then the MED-V column has to do with the value of the median value of houses in the neighborhood. So the idea is you would expect to see neighborhoods with higher levels of crime maybe have lower median values. Neighborhoods that have better schools might see higher median values. And I'm not suggesting that's the way it should be. I'm just saying that's what we might expect to see in some realistic data sets. So the describe function is able to take the data frame and all the values that are in it and say per column, how many rows do we have? What's the mean? What's the average value? What's the standard deviation on average? How far does each point differ from the average value? What's the minimum value? The various percentiles, what percent of the data has that value or less. So with one function call, you get quite a nice summary of the statistics of the data set. You are also able to grab, say, a particular column. So again, this is one of the nice things Panda does. If I want to look at the average median value of the homes, you'll see that on average, the homes in these data sets are $22,500. So clearly, this is quite some time ago, and is not a current value for housing prices in the Boston area or any area for that matter. There's another thing that you can say, df.shape. Once you have the data frame, you can ask for its shape, and it will return a Python tuple that indicates, in this case, there are 506 rows and 13 columns. So this is just a quick overview of the kinds of things that are available. I am now going to stop sharing this screen and switch over to my my Azure notebooks. So feel free to follow along. Get out of this. And so now I'm hoping you can see my my Jupyter notebooks. So let's go back to the process. If you go to accounts.microsoft.com and register to get an account, then you can log in. Once you log in, if you go to the link that we shared, which I will paste into the chat. So let me go back to Sarah's. So if you go to this link, this will take you to Sarah's view. And you can tell that you're in Sarah's view because it says Home, sGoodles, Projects. This is her view of a shared public Jupyter notebook. Jupyter notebooks don't have to be public, but this one is. So then if you just say clone it, once you're logged in, then it will take you to your version. So my version of Sarah's clone, basically, I can tell that I'm looking at this because it says home to my projects, not home to Sarah. And it tells me where did I clone it from. I cloned it from this here as well. So Hopefully, everyone can get this far. But after that, what you're seeing then is your version of a directory, which has a series of files in them. These are called IPython notebooks. And the IPython notebooks have the ability to, again, have all these cells and things like that. So we're going to go through just the first part, and I'm going to walk you through this. So please feel free to follow along. But the idea is also that you can continue to play around with these after the session's over. As Rebecca said, you'll have access to the video. If I said something and you want to go back and revisit it, please feel free to do so as well. All right. So if we click, again, this is our directory. If you look under the data directory, you'll see that there's a series of files there. If you go back and look at the images, again, you don't need these images, but these are available to you to reference within the documentation portions of your Jupyter notebooks as well. So if you are following along, please go to Cleaning and Manipulating Reference. It may take a second while it reads it in, but eventually it should pop in and show you what's going on. What we see here is the first cell is highlighted. We know that it's highlighted because it's got this blue ring around it. And so this is telling us that we are going to be working on some manipulating and cleaning the data. We're going to be working with data frames. So the first code sample is here. Now, all these commands up here allow you to add cells, remove cells, copy and paste things. But I want to start with, I'm going to restart and clear the output. This is a persistent process, right? So once you introduce a function or a variable name or something, it's available to you in this instance of the cell. Eventually, if you just left this running, it would probably spin down because nobody's using it. But when you log back in, it will be able to spin back up and sort of keep track of where you were. So this is a stateful approach. The first cell, once I select down here, is a code cell. And notice the green versus the blue. You're able to click on any cell you want, but just be mindful that if you try to run something further down that references something that you should have been mentioned above, it may not run. So if I run this iris df info, notice it says, I don't know what you're talking about. Iris df is not defined because it was defined in this cell here. One other thing, just because people who are new to Jupyter Notebooks always do this, if you find yourself accidentally double-clicking on one of the documentation cells, it will go into an editing mode using Markdown. You can get out of it either by hitting Shift Return or hitting the Run button here, and you'll notice that re-renders the data and advances you to the next cell. So again, hopefully everyone is able to follow along. If you're not up and running, again, try to just follow what I'm doing, and then go back and reclone things from the video after the fact, or reach out and I'll be happy to try to help you with that as well. Okay, so the first thing that we're going to do is we're going to import pandas. We're going to say as PD. It's just a convention for having a short name for referring to the namespace. And then we're going to pull in the scikit-learn datasets package. In there is a function called load iris. That's going to load in the iris dataset that we talked about. It's not loaded into a pandas data frame from scikit-learn. Like I said, scikit-learn does not depend on pandas, but this is just a available dataset for you to play around with. There are several that you can look through, and the iris object that comes back is in the format called a scikit-learn bunch. So if you want to know what's in there, feel free to Google scikit-learn bunch, and you'll be able to learn more about the data format there. But it's basically a key dictionary of values. There's a field called data, which has the rows. So each of the 4 samples that we have per iris, and then the names of those features will become our column names. So we can just assigning a Python list of values to the column names. So at this point, notice when you run it, there may be a brief period of time where there's an asterisk in the square brackets instead of a number or a blank. That tells you that the cell is running. And so you need to wait until that shifts into a number in order to know that that cell is done executing. So at this point, the code cell has executed, and it has moved on to the next cell, which is the documentation cell, which if you just run the documentation cell, it will advance to the next one. And so now I'm able to invoke the info method on the Iris data frame, and I can see I have 150 samples from 0 to 149. I have 4 columns, sepal length, sepal width, petal length, petal width. The data types associated with this are floating type numbers, and you get a sense of how much memory is being used. So this is obviously not a very large data set. I think probably the largest data set I've dealt with in pandas is probably about 2 million rows. Once you start getting beyond that, you're probably going to want to deal with something that pages the stuff in or works with clusters in the cloud or something like that. So, 2 million rows sounds like a lot, but by today's standards, that will fit in memory easily and is not what we would refer to as big data. So certainly 150 rows is not anything to worry about. All right, so I said the head function allows us to see what's in the data frame. We have the first 5 rows. We see that they're sepal length, sepal width, petal length, petal width. And there is a number called n, or a parameter called n, which allows you to specify which, how many rows do you want. So you can specify it by name, or it's the first positional one. You can just say, I want 10 rows. So if you wanted to see more than the default 5, you can customize that. Now, the first little exercise that we want you to do is to figure that out. But in case you're not familiar with this, you can say help dataframe.head, and this will tell you, Iris df head. This will say, okay, this is the method head in this panda section. Notice it says n is the first and only value, and it has a default value of 5. So that's how you would learn what arguments were available as well. So tail is a way of looking at the last couple of rows, and tail also takes this number. So if you want to see the last 10 rows in the results, you're able to do that as well. In terms of missing data, I'm going to create a NumPy array. I'm going to have a number, a none, and then 2 other numbers. Notice NumPy's array, n-dimensional array, has no problem storing a missing value. But what happens when I try to sum that up is it says, hey, you can't add an integer to a none type. So one of the things that you need to do is to potentially get rid of the missing values, and we'll see that. Now, none is a Python object. It's a marker to indicate a missing value. np.nan is an actual IEEE floating point standard for indicating a non-existent or something that isn't a number. So the problem with this and why we want to clean it up is if you say non plus 1, that returns non, non times 0, that returns non. So basically we don't want these numbers in there. If we create a series, which is, you can kind of think of as like our indexed collection of values, a data frame's columns are really a collection of series. In this case, I'm creating a series with the values 1, 2, and 3. And if I look at them, notice I have the values 1, 2, and 3. It's got a default positional index here. So position 0 is 1, position 1 is 2. So if I want to look at what's in the value of position 1, I could say, give me that, and we'll see that it's the number 2. So what this is then showing us is if you explicitly set the value to one of those things to be none and revisit it, notice up here, the first time I ran this, it said the data type of the series was int64 because these were all integers. Therefore, and I asked for it as an integer version. Therefore, the series is a collection of integer values. Once I switch in and add in something like np.nan or none, it will promote that to a floating point version, and it converts the data type as in that sense. So we're now dealing with floating point numbers instead of integers. So just be aware that these sorts of conversions can happen there as well. So let's look at the final example before we look at some machine learning stuff. Let's create a series and store all those crazy collection of values that we saw earlier. An integer, not a number, an empty string, and the Python none object. If I say is null on that, this is going to return the rows for which this is true. If I wanted to invert that, I could say not null. And notice it's going to say, okay, well, row 0, or the first value is not a null. The second one is, the third is not a null, the fourth one is. So depending on how you're thinking about your data, you may want to use is null or not null, but they're just Boolean inversions of each other. Now, the final thing that we're going to look at here is to drop missing values. You could say just drop them, and notice we now only have 0 and 2. 0, the first row in the series, because the number 0 is not missing, and 2 because it's a string. It's an empty string, but it's still a string. So notice once we get rid of not a number, then we now are no longer considering the data type of this series to be floating point numbers, but objects, because we have both integers and strings in them. But obviously we can't add numbers like that up as well. So the point is just simply, we have to go through the cleaning process, and Pandas is going to give us the ability to do that. So do spend some time going through this exercise. As you can see, it goes on. It gets you to deal with forward filling of results and backward filling in results and adding in the average values of things. So this will be a good exercise for you to work through the various capabilities that Pandas gives to you for dealing with missing data. But I want to get on to the meat of the class, which is on the machine learning models, to give you enough confidence that you can go through and play around with the notebooks yourself. So once we've read the data in, once we've collected it, once we've cleaned it up, then we're going to try to find evidence in the data that is associated with the thing we're trying to predict. And that's usually one of a series of activities. One is called a regression prediction, which is generally a continuous collection of values, produces a continuous output value. Or the other step might be a classification. So customers like this are also like customers like that, right? So we're trying to put you in a category so that we know how to think about you. And that's important, because if you're dealing with, say, a luxury-oriented customer, and you then try to treat them like they're a budget-minded customer, they're going to feel like you don't understand them very well. So we want to see customers that we've seen in the past who spent this much money, who spent this much time on our site, tended to behave like this, right? We're going to put them in one bucket. So if a new customer comes on and starts to behave like that, then we will maybe be able to start to think about them like customers we've seen in the past. Now, if you've never seen a customer behave a certain way in the past, then you're not likely to have good predictive abilities. You have a new type of customer, maybe who spends more or spends less, or tries to game the system or something, right? If you don't have that in your training data, then you're not going to be able to predict a category of customer that you've never seen before. So that's where you'd have to go back and collect some more data and retrain things and redeploy the models in order for it to be useful. So when we talk about looking to the past to learn from, we're generally saying we need data that looks like the population that we're going to reason about, which is why if you're trying to make sales predictions off of sales figures from 20 years ago, then that's not going to be very useful in dealing with where you are as a company today. So we need that process of training, deploying, updating the models, redeploying to be part of the process. All right, so one of the simplest kinds of things that you can deal with are called linear regressions. And this is when you collect data that has a certain shape to it, kind of a linear shape to it, hopefully. You're going to be able to substitute the actual values for the parameters of a line. And that may not be obvious until we see some examples, but you'll probably remember from your junior high or high school days, if you've ever studied the equation of a line, it's y equals mx plus b. What we're saying there is the b is the intercept, right? It's where it hits the y-axis, and it gives you a sense of how up and down the line is shifted. And then the m represents the slope of the relationship between the feature on the x-axis and the feature on the y-axis. So we're representing a line through the parameters y equals mx plus b. Now, because we might have more than one feature, you'll often see in machine learning this generalized to be beta naught, which is the offset, beta 1, which is the coefficient for the first feature, possibly beta 2 for a second feature, beta 3 for a third feature, and then the error, which is the difference between how good the predictive model could be and reality. Because there's probably always going to be some kind of contribution that you're not aware of, that's not part of your model. So we're just going to assume that there's some error constantly in what we're dealing with. And our goal for machine learning is to try to minimize that error. So let's see this in practice, and I think it'll be a lot clearer. We're going to read in the data. So we're going to use pandas to convert from a spreadsheet into a data frame. We're going to pull in NumPy for the numeric handling of the arrays. We're going to use a visualization library called matplotlib, which it's a very expressive, simple to use visualization library. But because we're running the code against the backend servers in the cloud, it doesn't necessarily know that if you're rendering an image back there that you want to show the image in your Jupyter notebook. So this little command here, %matplotlib inline, is the hint to Jupyter notebooks that says, hey, by the way, if somebody uses matplotlib to render something, serialize the results back and show it directly in the DOM here as well. And then we're also going to use a visualization library called Seaborn that builds on top of matplotlib. That has it's kind of an opinionated visualization library. So it looks to do things in a certain way. So notice I'm running this. The asterisk is running. It's now done running. And at this point, I can reference PD, NP, PLT, or SNS. Now we're going to read in the Boston housing data set here. And then we're going to print it out. So we'll look at the head. We'll see that the average income. Oh, I'm sorry. This is a newer data set than the Boston housing data set. Sorry. The average income of the person at the address, the average age of the house, the average number of rooms, the average number of bedrooms, the area population, the price of the house, and then the address. So if there's like something about the postal code that might be correlated with a particular, fancier, Tony neighborhood, maybe the address has some kind of input. Obviously, the number of rooms, the bigger the house is, the more expensive it's likely to be. People who make more money probably live in more expensive houses in general, unless they are, they just like saving their money and not spending it. So you may find that, somebody might live in a very small, cheap place, but still make a lot of money. But in general, I think we would expect to see the higher your income is, you want to live in a nicer place. So we would expect there to be some kind of connection between the inputs and the outputs. So ultimately, the thing that we're trying to learn is which aspects of these inputs correlate with the output, in this case, probably the price. So we would expect that one to, and maybe the age of the house. Maybe older houses aren't as nice, unless it's like a really old part of town, in which case it's a historical and there's a lot of cachet around it. So you might expect, up to a point, older is a negative impact, but then if you go very old, it may become a positive impact on the price. But again, what we're really just trying to do is to find a way of representing in a model, in this case a linear model, a way of making predictions about the data. So let's go ahead and get a summary of the fields. As we said, the describe field, or the describe method, prints out the count, the mean, the standard deviation of each of the columns. But oftentimes people prefer to see the transposed version of the describe, which is just a matrix manipulation to show us the average area income and all the individual features spread out here. So if the column names are long, you might want to like put them in this one column over here, and it makes it easier to read the data or more of the data that way. There's no right or wrong answer there. It's just a way of dealing with it. So when we look at the average income, area income, we'll see that we have 5,000 rows. We have 5,000 of each of these. So in this case, we don't have any missing data, but if we did, we might want to go through and fill in the missing results if we could do some research, or set them to some value, set them to the average value. Those are all the policies that you might choose based on the mechanisms that we talked about in the data cleansing portion of it. So what we see here is that the minimum area income is 17,796, and the maximum value is it looks like 10 or 100 times more than that. So we're talking about a range of incomes. The average, the minimum value of the age of the houses is like 2.6 years old, and the maximum age of this data set is 9.5 years old. So we're not talking about a wide range in terms of the neighborhood ages. So if that's the case, maybe we wouldn't expect there to be as strong of a connection between the age and the price. But if we're talking about 10 years, 20 years, 30 years, then we might expect to have more of an impact. Now, this is nice that these summaries are available. I tend to get a little overwhelmed, just like numeric noise. So, I'm a more visual thinker. So it's nice to be able to just very quickly look at the distributions of the values that might tell us something, right? So the Seaborn visualization library has a distribution plot. I'm going to pull out the series that's associated with the price column. So we're going to pull out the series of values there and then do a distribution plot of those. And what this shows us is that there is what's called a normal distribution, right? Normal distributions look like this bell curve, and the average value goes down the middle, but so does the median value, which is the middle 50%. So you can say 50% of the data, in this case, has a value of 1.2 million or less, and 50% of the data has 1.2 million or more. Notice the further away you get from the mean, the less likely that is to be the case. So this kind of distribution helps us reason over the likelihood. And if it's been a while since you studied statistics, I'll just remind you, within one standard deviation, which is just a measure of how far off the mean the data is, 68% of the data will fall in that range. Within two standard deviations, 95.5% of the data will fall in that range. And within three standard deviations, 99.5. So this becomes a tool that we can use if we're trying to build some kind of statistical model. But for our purposes, it just shows that the data is fairly evenly and normally distributed, which for the type of analysis that we're going to be dealing with is important. Linear regression doesn't work well if aspects of the data are not normally distributed. Let's pick two columns, and let's do a joint plot of the average area income versus the price. And notice, this is showing us the distribution of the average area income and the distribution of the price. And notice they're both normally distributed. So that helps us out in terms of some of the reasoning that we might want to deal with. If one was and one wasn't, then we would have to probably do some feature engineering to make the data make more sense. But in general, what we notice here is the higher the average income, as we go to the right on the x-axis, notice the price goes up, which corresponds to our expectation that people who make more money are going to want to live in a nicer neighborhood. Coincidentally, the lower the average income of the people in the neighborhood, the lower the price of the housing as well. So this, it doesn't look like a line. It looks kind of like an oval turned on its side, or rotated a little bit. But in general, we see a trend, and that's a good sign that there is a linear element to the data. Therefore, we could use a linear model like linear regression to represent the data. So it's not always clear where there are these kinds of relationships. And what we want to do is we want to see where those relationships might exist. So we said age might be correlated with price in a linear way. Number of bedrooms, number of rooms might be correlated in another way. So in essence, what we're doing is we're now saying for every feature that we know about, let's build one of those pair plots. And obviously that's a lot of computation and it takes a while. But what it shows us is like here, we're looking at average income and comparing it to average house age. So that does not have a very linear relationship whatsoever. We looked at area income and price, and we see that there is there. We see that there's a little bit of a connection between house age and price, not as strong as that. And then maybe the number of bedrooms you might think would be linear, but the problem is bedrooms are not a continuous value, right? You can't have like 3.6 bedrooms. So instead you have 2 bedrooms, 3 bedrooms, 4 bedrooms, 5 bedrooms, and those are discrete values. So when we do that comparison, notice we have a continuous distribution of values in the price range, but a discrete number of values in the number of bedroom ranges. So number of bedrooms and number of rooms, we would expect to see those kinds of banding in the data. But with one line of code, we read in the data, with one line of code, we can compare the data to each of the individual features and help us identify the strongest, most likely candidates for a linear relationship. So it looks like average area income and average age and area population have maybe some of the strongest linear connections between the feature that we're trying to predict, which is the price. If you're wondering what's going on down the diagonal, this is a common way of filling in what would otherwise maybe be a blank cell, because what this would correspond to is average area income and how it correlates to average area income, which obviously would be a straight line. So instead, they choose to either label it or leave it blank, or in this case, Seaborn shows you the distribution of values in the data set. So this is, you've read the data in, you weren't super familiar with it, you got some familiarity with it by looking at the describe function, looking at the statistical distribution of the values, visualizing them, finding where there could be linear elements in there. So now let's go ahead and try to predict the results. So this is what we call fitting the model. We're going to have the training data and the test data. We're going to have the inputs and the outputs. The inputs are generally called X, and the outputs are generally called Y. You may also hear them called features and targets or outputs. So in this case, just for convenience, we're going to call it X and Y. That makes your code much easier to read because people will know, okay, the X columns are the features, the Y column is the output. This syntax right here comes from Python NumPy area. It's just saying I want all the rows. So start at the beginning and go to the end. There's no constraints on the rows, but I only want the first 5 columns. And you may wonder, why do we only want the first 5 columns? Let's go back, look at our data frame. When we did the head, column 0, column 1, column 2, column 3, column 4, those 5 columns are the things that we're going to try to have as our feature inputs, and then the price is the thing that we're trying to fit against. So we're grabbing all the rows, the first 5 columns, and that's going to be our X data. And then the price is going to be our output target data. So once I read this in, I have segmented the data in such a way that X now refers to a data frame that just has the inputs, and Y is a data frame that only has the output. Now, the next thing we want to do is to split it up into training and test data. That is a tricky discussion in and of itself. Fortunately, we don't have to really talk about it now because there's a convenience function called train test split. So this allows you to say, here's my inputs and here's my outputs. Give me a test data set where 30% of the data is considered test data. That means 70% would be training data. There's no right or wrong answer in terms of what those look like. It could be 80-20, it could be 75-25, but you want to train on as much of the data as possible and yet still have a reasonable amount of data to test off of. That's a whole nother discussion. You can go through cross-fold validation, and a bunch of other stuff to look at how you split the data up and how that impacts your capacity to learn from the data. But that's something for you to investigate or to focus on in a different class. For our purposes, the train test split is just going to take all the rows and then break them up, and it's going to return what's called a Python tuple. And in this case, the Python tuple has our input X data, training data, and our input test data, our output training data, and our output test data. So we're going to destructure all those from the tuples and then assign them. And now here's where the magic is going to happen. So let's run this cell. We've now split it. Let's say I want to see, let's insert a cell below that. If I look at my X train, notice this is still just a data frame, right? It's a data frame, but it only has some of the data, right? If I look at X underscore train.info, we'll see that we have 3,500 entries. If I look at X test info, so these are the inputs for the test data, see that I have 1,500. So roughly 1/3 of the data is now test data, and 1/3 of the data is training data. I'll see the same split with the Y data set. So we've read it in, we've visualized it, we've split it up into training and test data. And now it's going to randomize that in all likelihood, because otherwise the data set might be sorted in some way where if you train off of the first 75% and test off the last 75%, maybe the last 75% happens to represent the more expensive neighborhoods, in which case all this work is for nothing. So that's the nice part about using libraries like this, is it already does the shuffling for you, so that's just not an issue. All right, so we need a linear regression implementation. We can pull that in from the scikit-learn linear model package and create a new instance. So at this point, it's been initialized with all the default values, and we're ready to train. So when we talk about machine learning and scikit-learn, that usually always happens with a fit function. If you see a fit that takes two parameters, and it's X and Y in particular, then you know that this is a supervised learning activity, because supervision connects the inputs to the outputs. Unsupervised learning is basically, here's my data, tell me something about it. And unfortunately, this is not real artificial intelligence. Therefore, the best that we can do with unsupervised is usually to find clusters or anomalies or things like that. So for the most part, you're going to be playing around and experimenting with supervised learning. So at this point, if I run this cell and do a fit of the X to the Y data, that's as fast as it's done, right? We're not talking about a lot of data. So it went through and it did some math behind the scenes. But what it did is it tried to find a way of connecting those features to the outputs. Now, you may be confused because we're not talking about one feature and one output, but you can imagine it did that per feature for each one of those. So we have now coefficients that are associated with the process. And if I look at reg.coefs underscore, this is an, oops, sorry, coef. This is an array. For each of the features that we have, we see that there's a separate m, a separate slope. So the first column, the average income, has a slope of 2.15. So basically, for every increase in income, the price of the house goes up by a factor of about 2.15. So that's a pretty strong connection. For every step that we go in the age of the house, we see that increases the value of the house in some way. So this is what's going on behind the scenes, and then the coefficients combine to give you a linear model, even though there's more than one feature, which confuses people. But the thing to remember is it has to do with the linearity of the coefficient and the feature. So it's beta 0 or beta 1 times x1 plus beta 2 times x2. So beta 1 is this, beta 2 is that, but they are linearly related to the feature. All right, so we've trained our model. It's figured out some coefficients and intercepts for us. Let's see how well we do. We trained off of our x inputs and our y output, or our training inputs and our training outputs. Now we're going to plug in our test inputs, which again is our x data, and that's going to make some predictions. And if I look at the predictions, it will say, okay, for the first row in the test data, I think the house is going to be $600,000. For the second one, I think it's going to be $1.8 million. So these are predictions. But keep in mind, we also have actual values, right? Sorry, what did I call that? Lowercase y. Y test. So we can see this is what the actual values that we collected from our data set are. And so what we really wanted to see is how do the individual predictions differ from the actual values? And if they are, on the whole, relatively small, then we feel like we've learned something, right? Our machine learning model has captured the nature of the relationship. So if I print out everything together, we'll see that in algebraic terms, our model is negative 2.6 million plus 0.258 times the first one. Sorry, I guess that was to the negative one. I didn't notice that. So it's basically going through and adding up all these coefficients. And the thing to remember here is each of these features might work against us. You might have a newer house that's smaller or an older house that's bigger, and those individual features would have us adjust our expectations in the price predictions. So it's really how do they all combine together is what then helps us take a guess as, a house that's this old with an average income of this, with this number of bedrooms, with a population of this, probably will fall around here. So there's, again, lots of ways that you can measure the success of a modeling system like this, but there's a scoring mechanism. It's the R squared score, and we'll see that this comes up with a 0.92. So the closer you are to 1 with this, the better, but it's a measure of how much of the variance in the data does the model predict. Because again, if there's a strong linear component and the model does a good job of making predictions, then more of the distribution of the data will be predicted by the model. If the data is noisy and doesn't have a linear element, you would expect a much lower R squared score. So just as a quick summary, this is a way of measuring the quality of the predictions that a linear regression model is doing. Now, as a quick another check, we could say let's do a distribution plot of the Y test data minus the predictions. So again, for every X test row, we have a Y output and a prediction now, and I want to measure how far off they are. So I'm just going to subtract one from the other, and we'll see that we end up having a normal distribution of error. What that tells us is the majority of the values are 0, meaning most of the predictions are actually quite good, right? some are a little wrong on one side, some are a little wrong on the other side, but there are very, very few that are very wrong, which means that it's actually, with a 0.92 r squared, given how little effort we put into it, is actually a pretty reasonable model. Now, if the error were not normally distributed, then this would not be a good use of linear regression, and we would expect to see a much worse result. So if you try taking some other data that does not have these kinds of linear relationships in them and try to build a linear regression model in it, you should expect to see a much different shape in the results. But for the most part, we're saying the older a neighborhood is, the higher the income is on average, the higher the number of bedrooms. Those all have a series of linear relationships in them. Therefore, a linear regression model should do a pretty good job. We can also take and compare the y-test data and the predictions themselves as a scatter plot, and you'll see, again, as we increase our values for our y-test data, we see a corresponding increase in the values in the predictions. Therefore, there's a pretty strong positive correlation between our predictions and our actual values, which again corresponds to the linearity that we saw, the relatively high r-squared value, etc. Now, in terms of seeing the individual points, this little section here is just saying, because they're all stacked on top of each other, it's hard to see. So one of the things that you can do, and one of the things that makes scikit-learn and Seaborn so nice, is it's really easy to change something like the transparency values. So where there are outliers, then we're just going to kind of blend those into the background. But where there are more data points stacked on top of each other, the color contributions will contribute to be a higher saturation in the visualization. So it's just a way of looking through this. So I know there's a lot to go through if this is new to you, but hopefully the combination of the video and the notebooks are going to give you the ability to go back through this and see what's going on, and to play around with it and to familiarize yourselves with the libraries. If there are any questions, please feel free to toss them into the Q&A section. It'll take a while for those to kind of show up and be visible to me. If there are, I will come back to them. But I want to move on to another type of machine learning model that is also linear in nature, but is even though it's called a logistic regression, it's actually a classification. There are complex reasons for that. In general, we're usually talking about regression or classification. This is called logistic regression, and it is a type of classification. It's the only one that you really need to worry about. But the idea here is, if I can build a line based on the various inputs, and you end up on one side of the line or the other side of the line, then I want to draw conclusions about what class you would fall into. One of the nice things, like with the iris data set, is the Setosa class is genetically distinct from the other ones. So if you start to do scatter plots of the features, you'll see the Setosas are off doing their own thing. So you could build a logistic regression to separate the Setosas from all the other ones, and at least build a pretty good classifier for whether something is a Setosa or not. If you stop and think about it for a second, I hope it's clear that a line really only allows you to separate between two classes, but you could have as many of these lines as you want, right, to separate with different features, and that may help you build a more complex view. But we'll also look at very quickly at another example called a decision tree that works with that. So for this data set, I'm going to go through the early parts of it pretty quickly because it's very similar to what we've done so far. This represents a subset of the passenger data on the Titanic. For every passenger, we know their ID, whether they survived or not, encoded as a 0 or 1, and what class did they travel in, first class, second class, third class. We also know their name, their gender, their age, The SIB-SP column represents the number of siblings and spouses that they were traveling with. And why that's important is if you're part of a large family and as the boat is going down, you come across a lifeboat. If there are 5 people in your family, but there's only 2 spots in the lifeboat, this becomes, kind of a moral quandary. Do we break the family up or do we go look for another lifeboat? And if there weren't enough lifeboats, then that would obviously have a material impact on whether you survived or not. So that's one reason why that's encoded in the data set here. And then the other one is the parent-child count, like how many parents and children were traveling together, in part because that's probably a tighter bond. Like it would be less likely for parents to separate from their children than maybe 2 siblings that were in their 20s. You go that way, I'll go this way. We'll see you wherever, hopefully. And so again, different elements of the family composition and who's traveling together could have an impact on whether you survived or not. So if we look at the overall info for the data frame, we can see that we have several more rows. We have close to 900 rows. We don't know the age of everybody, and we don't know what cabin most people were staying in. It's just those records aren't available. But for the most part, we know the different values for each of the things. But in order to try to build a logistic regression model, which is still going to be linear in nature, we kind of want more consistency in the data. So we're going to drop rows that have, or columns that don't have any real useful purpose to us. We're going to drop things that probably won't have any predictive results, like what your name was. Obviously we don't have a way of turning that into numbers, but even if we did, John Jacob Astor was the wealthiest person in the world, and he was on the Titanic and he died, right? So clearly names didn't help that much. So what we're going to do is we're going to drop the name column and we're going to drop the ticket column. For the most part with pandas, unless you specifically say to do this in place, it will return a view of the data. It'll leave the original data frame alone. So unless you say df equals df drop that, you won't actually change anything. Here, because we're saying in place equals true, we're actually mutating the data frame itself, so that's fine. And then the axis 1 means we're dropping things from the column axis. Because rows could have named indices as well, we need to make sure that we're being specific about which axis are we dropping off of. So we're dropping those columns, and then we can do some of our pairwise comparisons to see what fare did you pay and did you survive or not. Now, obviously, survival is, in this case, a discrete set of values. You either did or you didn't. But what this is saying is, people who had lower fares tended to not survive. People who had higher fares did tend to survive. So, the narratives around the process, people in first class were closer to the surface. There were more lifeboats for them. It was easier for them to get into. They were given preferential treatment. Lots of reasons why what class you were traveling in might correlate with the results. But one of the interesting things that you can do is to go through and analyze the data, and you'll see very clearly that women and children first was a thing in all the classes. And you can do that by analyzing the data, grouping by class or age and gender and class and gender, which I will leave as an exercise for you. It's very similar to the stuff that I'm going to wrap up with here. So let's do a pair. You can go through and do pair plots of other things like did sibling and spouse counts impact. Again, notice the higher number of people who were, most people had a lower number of sibling and spouses, right? They're either traveling by themselves or just 1 or 2 other people. But the ones who had higher numbers, we tend to see survived at a slightly lower rate than other ones. But let's wrap up now by looking at what we can do. We can group by the survived column and then take the mean, and that will go through and say, okay, well, on average, for those who didn't survive, the average passenger class was 2.5. Now that's just a funny way of saying you were either in second or third class, right? Because first class plus second class plus third class divided by 3 would come out that way. So the higher your class, the less, in this case, the lower the class, because the higher number, right? The less chance that you had to survive. Notice that because of the women and children skew, the younger you were, the higher the chance that you were to survive. But keep in mind, we're mixing all the people together. So you need to go through and tease these things apart to see what the actual contributions are. And so I could go through and say, let's break it up based on age. So a very low age, this person survived. Very low age, this person survived. So notice we see a lot of survival down at this rate, and the higher the age, maybe less so. So again, women and children, the impact of age with respect to whether you're a child or not can have impact on survivability as well. So if you go through and we study the data, you can look at how many values are there for each individual field, how much data is missing. This is a fairly compact way of saying, find me any columns that have more than half of the data missing. And really the only one that we see is the cabin. So this says, find me all the is nulls. Those are going to be true or false. Remember, sum them up. True is 1, false is 0. So the sum of the values tells you how many missing values there are, how many missing rows there are. And then we're doing a comparison against the length of the data frame divided by 2. So did any of the columns have more missing values than not? And it turns out the cabin was there. So your choice is either to go do some research and find out what cabin everybody was in, which is unlikely given the nature of the data, or just to go through and drop it like we've seen. So let's drop that, look at the info. We'll see that we have missing age ranges. That's the biggest one. We can fill that in by looking at the distribution, and we'll see that there are more. We see that there are 177 missing results there, and if I look at the distribution of age and gender, we'll see that per females and males, the median value is slightly skewed towards the males. So if you're going to fill in missing results, you might want to say, okay, well, if you're female, I'll fill in with the median result of the female median values. If you're a male, I'll fill in with the median value of the male values. If you start to mix them all together, then the fact that gender was such an important correlation to survivability, you wouldn't end up seeing that here. So walk through the results, but in the end, we're going to go through the train test split. We're going to have the inputs and the outputs. You're going to break it up with the same or different, depending on your preferences. I want 30% test data, 70% other data. Build the logistic regression, fit the inputs to the output, generate some predictions, and then evaluate the results. So we're running out of time, and I want to leave some time for questions if there is any. But again, the nice thing about Jupyter Notebooks is that they have narrative around them. So as you walk through the lessons, you can figure out what these things mean. If F1 score doesn't make sense to you, go Google it, look it up. You'll learn what an F1 score is in the results. So we've shown you one example of using a linear regression model, and we've shown you one example of using a logistic regression model. Ultimately, they're both trying to find linear coefficients. It's just in one sense, we're trying to predict where are you on the line. In the other sense, we're trying to build this complex mechanism that says, are you on this side of the line or that side of the line, and try to decide whether that is going to correlate with your survivability or not. So the classifier could easily be done using a decision tree as well. So it's a different approach, but it's basically saying, look at each feature, and is there a pivot point where the feature says less than this value means you probably will survive, greater than this value means you probably won't survive. And by asking the right series of questions, it can try to make these predictions for you. So I'm going to let you go through that, but the thing that I want to make clear is the information that's available to either of the classifiers is the same. It's all contained in the data. It's just a question of whether the model absorbs more of the data to help you make decisions from, right? Data is just a distinct value, one from another, whereas information actually helps us resolve uncertainty. So if I'm trying to decide whether somebody would survive or not, then the more information that I can use from the data that we've collected that's useful in a predictive way, hopefully the better the prediction model will be as well. So one final thing that you can do is to visualize the result. And I will just point out when you do this, it will pop up a little thing here and it'll look empty. Just scroll around in it and you'll see this very complex decision tree that was generated. And what it did was to say, if I look at all the features that I have, which questions should I ask first to try to make any kind of predictive results? And so the knobs that we have there are in terms of how many questions do you get to ask. One question is probably not enough. So we would say that we have a lot of bias error because one question is too much of an approximation. If I give you a full budget of asking as many questions as you want, then at some point I'll be down to, oh, is your name John Jacob Astor? Because he died. And at that point, you're just memorizing the details. So the takeaway message from a machine learning perspective here is, if you have, if you pay too much attention to an individual data point, then if that data point isn't in your population you're reasoning over, it's not going to be useful to you. You're overfitting and your prediction results will be very noisy. If you don't pay enough attention to the data, then you're not actually seeing the kinds of relationships that are in there. Therefore, the model is too much of an approximation. So we have this tension. It's called the bias variance trade-off. It really comes down to how much attention do you pay to the individual details and how much is the model too much of an approximation. So please, if you have any questions, toss them in. Otherwise, I encourage you to reach out on Twitter, and I'll try to be happy to walk you back through some of the things if you have questions. The video will be available, so hopefully, if I said something that didn't make sense, you can kind of go back and catch up. But otherwise, and then the remaining minutes, I want to see if there are any questions. And there can be a bit of a lag, so if it seems weird that I'm going silent, I'm just waiting to see if those show up. Okay, it seems. Go ahead.
Sorry, I'm just going to jump in here for a second and just share a couple of our upcoming events. And then if any questions arise while that's happening.
Okay.
Hang on one second. Here we go. Sorry, a little bit of technical with using this system. So just thank you all for joining us. Thanks, Brian, for putting on such a great workshop here. Again, if you have any questions, feel free to type them in while I'm just reviewing this. So we have lots of events all the time. And some of those events are localized to a specific reactor, while others are on a global scale where we're doing it across. It really depends on time zones and timing. We try to parse out things that are happening primarily during business hours or around that window. But if you happen to wake up early or go to bed late or work nights, you might be interested in attending some of these other events that were featured. So it is recommended that when you're on your meetup page that you visit some of the other meetups that are all tied together with the Reactor, or visit us at one of our Microsoft page or follow us on Twitter. So certainly feel free to check out, some of the other reactors and options that exist, because we definitely don't have them all listed on individual calendars. We have some of them specifically listed on, location based. And then, yeah, sign up if you haven't signed up yet. Check out our different options and different things that are happening. If you have the opportunity, feel free to submit a survey, just reviewing the content, positive, negatives, what you'd hope to see in the future, things like that. And you'll just be asked what the event code was that you were attending when you're providing your review. So it's 7823. And just make sure that you supply that as well. Back to you, Brian. I haven't seen any questions come through.
Okay. One question that did come up was about the slides. Do you know where those are available?
So at the conclusion of the event, if you wish to share your slides with us, we will post them along with the YouTube video.
Oh, okay.
So we'll have a link to that. Yeah.
Then yes.
So you can check in on our YouTube channel, which I shared, and then most videos coincide with slides, and that will be in the comment section underneath the YouTube video. So I am not seeing any questions. As Brian indicated earlier, if you have questions in the future, you can always reach out to him on his Twitter account. And then otherwise, I think it's a wrap.
All right. Well, thank you very much for your time, everybody. Stay safe, stay healthy, and we hope to see you at another one of the upcoming events.